Okay, where is my, yeah. So what was said right now is something like this. If you have a differential equation of this form and many important differential equations that we will meet in quantum mechanics and in other branches of physics are also of this form, where, as Chan obviously said, this coefficient can be made to be 1 simply by dividing by whatever coefficient you have. And then the definition stated was, if P of x has a simple pole, okay, this is for what is called a regular singularity. First of all, okay, let's go in order first. First, if P of x and Q of x are both regular functions at x0. Now, functions may have singularities in different places. So, first of all, when you say there is a regular singularity or an irregular singularity of a differential equation, you of course are talking about a particular point where the singularity is. So, say at some x equal to x0, let's say P of x and Q of x are both regular functions. That means they're analytic functions in a sense. Remember, all of this is in complex analysis. So even though we are okay, sorry, how much of this did you really hear?
Sir, only the first line.
Which was the first line?
If px and qx are regular functions at x equal to x.
Oh, great. So I didn't even realize that I lost contact until nobody responded to several questions. Anyway, that's my bad. Uh, so if P of x and Q of x are regular functions at x equal to x0, what that means is P of x
Sir, you
can be
haven't
expanded.
started presenting.
Oh, you're right. Presentation also stopped when I moved on. Thank you. Okay. So now I hope everybody can see the screen with the Sunal file. That is the sheet on which I'm writing.
Yes, sir.
Okay.
Yes, sir.
So we started by saying that let us look at what regular point means first. So x equal to x0 is a regular point of the differential equation of the, okay, second order linear differential equation that we are dealing with. If this happens, P of x and Q of x are both regular functions, that means you can write P of x and Q of x as power series in x minus x0. Sorry, in a bad typo, which is of course x minus x0 whole square, x minus x0 whole square here as well, and so on, and higher powers. So if this happens, then we can write, we say that that the point x equal to x0 is a regular point. The question that I asked without understanding that nobody is listening to me then was, what does it really mean? When you say a point x equal to x0 is a regular point of an ODE, what does it mean as far as the solutions to the equation are concerned? Yes?
There is some solution to the equation which is analytic.
Some
Around
solution to the equation which is analytic.
around some I mean
Okay.
with some
Anybody with a
finite
difference
ranges
of
of
opinion?
convergence.
The solution can be expanded in a power series.
The solution, by when you say the solution, you mean one solution? Some, okay. Some, the, these are very precise meanings in mathematical parlance, so I'm not sure whether you're using that in that mean sense. So can you just clarify what you meant?
A solution exists and it can be uh, expanded as a power series.
Okay, good. So that's exactly what it means. Correct. If the point x equal to x0 is a regular point, first, what does it mean as far as the differential equation is concerned? Well, notice that if p of x and q of x actually were not regular functions, actually blew up at x equal to x0, let's say, that would usually mean that they have a zero denominator, right? At x equal to x0. Of course, you could have rewritten this equation by multiplying through by the denominator. But then what would happen is the coefficient of y double prime would have vanished at x equal to x0. So what this really means as far as the equation is concerned is that the equation ceases to be a second order equation at x equal to x0. What is a second order equation? It's an equation which gives you the second derivative of a function in terms of its lower derivatives and the value of the function itself, right? This equation, of course, if p of x and q of x were nice regular functions, it tells you what y double prime is. Y double prime is simply minus p of x into y prime minus q of x into y. But if p of x and q of x blows up, and that really means that the coefficient of y double prime actually was zero before you divided through by it, that means at that point x equal to x0, the equation gives you no information about the second derivative. That's really what not being regular means. Being regular means the equation is really genuinely second order. And a consequence of this, as far as solutions are concerned, is that, as was pointed out, both the independent solutions, there are two independent solutions, right? The second order linear differential equation. Both of these independent solutions are regular functions. They can be written down in the form of a power series, which of course is the basic idea behind using the power series method for solving differential equations. So that's of course starting a bit too far. Next we come to what if a point is not regular, then of course it's singular. That's just nomenclature. Singular simply means not regular. So if x equal to x0 is singular, then what does it tell you? It tells you that the equation actually is not really second order at that particular point x equal to x0. And as far as the solutions is concerned, what it tells you, okay, what does it really tell you, by the way? Okay, question, what does this tell you? If x equal to x0 is singular, what does it tell you about the solutions of the differential equation near x equal to x0? So the implication of x equal to x0 being singular for the solutions, what is that? That sort of is easy. That's just the opposite of what I said right now, or what actually you said right now, about what happens when x equal to x0 is regular.
Then at x equal to x0, the solution is blows up at this point. It's not finite solution.
Now let's be clear about what you mean by the solution.
The solution of this equation at x equal to x0 point.
Well, typically a second order linear differential equation would have a homogeneous second order linear differential equation, something with zero on the other side, would have two component solutions. So are you making this statement about both the solutions or about one of them?
Both of them at x equal.
One of the line.
So maybe qx is, or maybe p px, either
One of
px.
them, p of x and q of x, or both of them are singular, maybe, are singular functions, not regular functions. And I'm asking about the solution to the differential equation. What does this imply? You're on the right track, but let's be precise about it.
Not clear, sir.
At least one of the solutions should blow up.
Yeah, exactly. Burgal is right. At least one of the solution is not a regular function or not an analytic function. So this is what really means, and this is simply an exercise in negating a mathematical statement. If the mathematical statement was that if x equal to x0 is regular, then both solutions at x equal to x0 have to be regular. Then the opposite of that, or if x equal to x0 is not regular, what that has to imply is that at least one of the two independent solutions must have a singularity. Now it's possible that both of them may have singularities, but at least one of them must have a singularity. That's what a singular point means. Okay, that's what a singular point means as far as the solution is concerned. Okay, now then, as you all know, we break up singular points into two different kinds. One is a regular singular point, and the other one is, of course, the irregular singular point. That's just an obvious name for a point which is not regular singular. The question that I asked at the beginning was, what does it mean when you say an equation is regular singular? And the answer that I got was something like this. If p of z okay, we are sticking to simple situations where p of x and q of x, even if they are singular, they have poles at worst, nothing other than that. So if p of z has a pole which is not greater than or not greater than, okay, sorry, if p of l has pole, let's put it the right way, I'm talking of regular singular, then if p of z has pole less than or equal to degree 1, equal to degree 1 means, of course, simple pole, or if not a simple pole, then the function is regular. And q of z so this is the definition of regular singular point. Does everybody agree with that? Anybody disagrees? Okay, it seems that there is universal agreement on this score. That is, I've managed to remember my maths properly. But hasn't it ever struck you as strange as to why a definition of something as important as a classification of a differential equation should be so strange? Doesn't it look rather artificial? P of z has a pole which is not greater than less than equal to degree 1. Q of z has pole not less than equal to degree 2. What's so special about 1 and 2? Why not 3 and 4? Why not 20 and 25? Look, if we had many such classifications, then I could have understood this. But if we have just two different classifications, regular and irregular. What is regular? If pz has pole less than equal to degree 1 and qz has pole less than equal to degree 2. If not, irregular. Doesn't that sound like a bit of a, well, bad joke or something? It doesn't seem natural, right? Does it seem natural to anybody? Just because 1 and 2 are the smallest two positive integers. Okay, one answer is we can use Frobenius method for this case only. Why? That's right. But the answer, but the real, that is actually part of the fact that this is really not the definition. This is what we often do. This is not the definition. This is the definition that is given to you at the very beginning when you first study second order linear differential equations. Primarily because at that point of time, most of you have not done any complex analysis. So you wouldn't even know the real definition if somebody gave it to you. So what this is really not a definition, it's a criterion. Criterion meaning what? Meaning simply this, meaning if I wanted to recognize whether a pole is whether a point is a singular point, regular singular point or not, this is the easy way to tell that. Unfortunately, because in many courses, complex analysis is pushed to the end, so people don't really know what this means when they first encounter it and they have to go ahead and use it. This is often used as in place of the definition. Okay? This is not the definition, it's just used in place of the definition simply because the definition cannot be given at that stage. Okay, so the real definition is something else. The real definition again actually hinges on the nature of the solutions, not on the P of Z, Q of Z structure. The real definition simply goes this way. Just you could have defined a regular point to be one at which both solutions are regular and analytic functions. Of course, we have just now seen that if a point is not regular, at least one of the two independent solutions must have a singularity. The question is, what kind of singularity can it have? So since you have already done this amount of complex analysis, you know that you can have poles in a singularity. This is for the, now I'm talking about the solution, which or any general function can have singularities like poles, can have branch points. And the third possibility, the worst possible kind of singularity is that it's called an essential singularity. An essential singularity essentially means something like a function. We have already seen, okay, if you have watched the lecture, you have already seen an example, but still, a function like e to the 1 by z is essentially singular at z equal to z0, simply because if you expand this out, about z equal to 0, you get negative powers of z, but the point is you don't stop getting negative powers of z. You get as high and arbitrarily high up negative power of z as you want, and you get more. If these negative powers stop somewhere, you would have a pole of that order. But since the negative powers never stop, you have what is called an essential singularity. The worst possible kind of singularity that you can have. Okay? So, I'm stressing all this because these issues are going to be very, very important in the rest of our mathematical calculations involving various quantum systems. So, this is not quantum mechanics at all. This is just mathematical physics. Just a recap of that. Now, the point is, since essential singularities are so bad, we would love to have solutions which don't have essential singularities. Okay. Of course, if the point is regular, you don't have any singularities at all in your solutions, you're happy. If the point is not singular, then then the solutions, at least one of the solutions will have a singularity. Okay. And if we are lucky, then neither of the two independent solutions will have an essential singularity. Now, this being lucky is actually called, it goes by the name regular singular point. Your differential equation has a regular singular point. Okay, somebody said, can you, I just saw this off the corner of my eye. Can I talk about branch points? I will definitely talk about branch points because we will need to talk about branch points very much in the course, but not today. We'll talk about branch points more when we need them. Okay. But branch points, I'm sure everybody has heard of the branch points, right? These names, pole, branch point, essential singularity, all of these should be familiar, right? Okay. So we will talk about branch points in some detail. We will need to talk about branch points in quite a lot of detail for later parts of the course. And when we have a real context for that, we will talk about branch points. Right now, the one point I want to make is poles and branch points are singularities, but they're not that bad. Essential singularities are really bad. Okay. So we would love to have a situation where our solutions, even if not regular, are not essentially singular. And that's what a regular singular point of a differential equation is. A regular singular point of a differential equation is a point about which both the independent solutions are free of essential singularities. Okay? And if, on the other hand, the singular point is an irregular singular point, then at least one of the two independent solutions must have an essential singularity. Both of them may have essential singularities, but at least one of them must have an essential singularity. Okay, is that clear to everybody?
So could you please repeat the last sentence?
The last sentence was, we would want our solutions to be free of essential singularities, right? But we have two independent solutions to our second order differential equation. So if both of them are free of essential singularities, then you say that at that point, then you say the point is a regular singular point. And the way you can check whether a point is regular singular is using this criterion. Okay. So P of Z is a simple pole and Q of Z is a pole not more severe than degree 2 or second order, not worse than a second order pole. That is often stated as a definition of regular singular point. That really is a criterion for knowing it. Regular singular point is a point about which both the solutions are free of essential singularities.
Sir, how this criteria comes? Please say this.
How this criteria comes would take a lot of advanced maths to really justify, but I will give you a sort of crude answer to that. Okay, the full answer, anybody who is interested can read any standard ODE book. You should actually, because this is important information. One book which you might like to read is the one by Inch, INCE. I've forgotten the name of the book. It must be ordinary differential equations or something else. And there's another very good book by Birkhoff and Rota. So anybody who is interested in the full mathematical details of this, you should read either of the two. By the way, you already know much of what is necessary. For example, you should know that there is something you can work out for these equations called the Wronskian, right? And you can see if your PZ, for example, has a pole which is degree higher than 2 or higher, then it's very easy to see that the integrating factor that you have in the Wronskian is going to be extremely singular, essentially singular, and that since the two solutions are connected via the Wronskian, and you can find out one solution from the other. I hope you know this, right?
Yes, sir.
You know that you can, from one solution using the Wronskian, you can find out the other, right? Like
Yes.
doing an integration. And since if the Wronskian turns out to be essentially singular, it's guaranteed that one solution will be essentially singular, right?
Yes, sir.
So that's easy to understand, but to get to the full details will take some time. But I will give you a sort of hand-waving, reasonably good answer. Reasonably good meaning good at the mathematical physics level good to this later on. But let me just finish this point. An essential singularity is what you would love to avoid unless it becomes unavoidable, of course. And that is why regular singular points are the ones you love and you don't really want to have essential singular or irregular singular points. Sometimes you can't avoid them, as in the case of the harmonic oscillator, by the way. if you've gone through the lecture, you would have realized that the point I was trying to stress in the lecture is not really the details of the calculation. That's really not that important, although I did talk about the details. But this equation that you have, which is the Schrodinger equation for the harmonic oscillator after you do some rescaling and renaming of variables, here, of course, P of z is simply 0. There is no psi prime term. And Q of z is lambda minus z square, both nice regular functions at every z. So there is no singularity anywhere in this differential equation in the finite complex plane. Well, unfortunately, we cannot stick to just the finite complex plane. Infinitely far away, there is a singularity. And the way to check that, I mentioned that in the video, but I did not work it out. So that's an exercise that you should really do. Use z equal to 1 by u. Of course, remember that if you are doing z equal to 1 by u, it's just chain rule. There is psi prime, which is d psi dz. Of course, is d psi du times du dz. And du dz is then minus 1 by z square or minus u square du acting on psi. So d dz here is minus u square du. So basically, psi double prime becomes u square du, u square du acting on psi. Where I have, of course, made the standard basis mistake of, or, well, I shouldn't really call it a mistake because every basis does it, of not changing the name of the function and keeping on calling it psi, whether it's psi of u or psi of z. Now, you should be able to see that this immediately tells you that that our equation is going to be rather badly behaved, right? At u equal to 0. Because if you expand this out, what does it give you? You get u to the 4 d2 psi du2 plus 2u cube d psi du, right? That's what this derivative gives you. Plus, of course, this is not the entire equation. You have lambda minus z square, and lambda minus z square is lambda minus 1 by u square, psi equals 0. Right? So you should see that for this equation at least, P of u is 2 by u. Not bad. It's a simple pole. First order pole at u equal to 0. So singular, but not dangerous at this stage. But what about Q of u? Q of u is lambda u square minus 1 by u to the 6. Right? So this is really, really bad. This is a very high order pole in Q of u. So way beyond the criterion for regular singular points. So for my differential equation, u equal to 0 is an irregular singular point. And u equal to 0 is of course the same as z equal to infinity. So this is what really should worry us. We know before we start solving the equation that at infinity there will be trouble. Okay? This is the critical thing. It's not as if we are discovering these things as we go by and suddenly find out, okay, this solution is diverging and so on. We already know that as z goes to infinity, we would be in trouble. Okay? And this is the important point, that whenever you try to solve a differential equation, and you will meet several of these in quantum mechanics courses, you would have to be sure about where the singularities are, what kind of behavior you would expect near the singularities. If you proceed that way, it's much easier to understand why, say, some steps are being taken, why some particular substitutions are being done, and so on. Okay? Any questions about this so far? Yes, Sharon, sir, just sir, or was there something before that? Your mic is not working, so you wanted to ask a question? I will wait for you to type it out. Go ahead, type out the question. If anybody else has a question while he is typing out his, please go ahead. Nobody has any other questions? Okay, what is this? By the way, this is your problem sheet, which I'm not going to discuss today because this has just been uploaded. When there is an essential singularity, will both solutions have... Well, both solutions usually will not, or will often not. A point z equal to z0 or x equal to x0 is essentially singular for a differential equation if at least one of the two solutions is essentially singular. Both do not have to be essentially singular. Maybe. By the way, this particular equation, this one, as we saw by doing the asymptotic thing, has two solutions, e to the z square by 2 and e to the minus z square by 2. Well, these are not solutions. These are solutions. These are behaviors of the solution as you go very far away. So, which of these is essentially singular? Which of the two? As z goes to infinity. But watch the video. You should know the answer because there I tell you what the answer is.
Plus z square root. Plus z square root.
Plus z square by 2 is essentially singular. And e to the minus z square by 2?
In the complex plane, not in the real
Look,
part.
everything is complex, is on the complex plane. We may be interested in the solution finally on the real line, but all this discussion is on the complex plane. Okay, so on the complex plane, I'm sure many of on the real line this function is well behaved. On the real line, this one is badly behaved as that becomes very large. However, when we ask which of these two equations, these two functions are essentially singular as z goes to infinity, the answer is both of them. This is essentially singular as z goes to infinity, that's sort of obvious. That this is also essentially singular as z goes to infinity may not be that obvious, right? Because it seems like a nice function which you live with all the time, right? The Gaussian function, bell-shaped, and so on. Somebody wanted to say something?
Sir,
Yeah.
the truncated part is singular, and another part is finite value because at minus
Okay, I
infinity
don't
there
understand
is
what the truncated value part you're talking. I'm talking about these two solutions themselves. They are functions in their own right? Forget about the differential equation. These are two functions.
it's a second function that is in
E to the
positive
minus z square by 2. Yeah.
or in the total plane plus infinity and minus infinity, both are finite value. So that is irregular singular point.
No, I didn't get you. You seem to be saying several things, but okay, let me just clearly ask you this. This second function, let's focus. Are you talking of this function? E to the minus z square by 2. Yes? No? Sorry, your mic seems to be sort of breaking up. Are you saying something? I can't hear you, fortunately. Go try typing on the chat box then. Okay, sorry, I couldn't hear that, but I'm pretty sure I sort of heard, what I heard was only parts of what was said. So I'm not sure whether I heard it right. But it seems that the opinion was this function is okay because, of course, as z goes to plus minus infinity, it behaves like this nice bell curve, as it does. It falls off nicely to 0. And we are happy with it. And that would be right. If we stick to only the complex, only the real line, this function is perfectly okay. And this is the one we want. But that is not to say that this function is free of essential singularities. Because if you moved along the imaginary axis, then z would be ix for some real number x. And then this function will become e to the x square by 2 plus x square by 2. Because I square is, of course, minus 1. And then if you moved along the imaginary axis very, very far away, this function will blow up badly. So this one blows up badly on the real line. This one blows up badly on the imaginary axis. But the complex plane, if you look at the whole complex plane, both of these functions are badly behaved. Okay? So that's the point. In this, for this particular differential equation, that is for psi double prime plus lambda minus z square psi equals 0, z equal to infinity is an irregular singularity, singular point. And not only that, both its independent solutions are badly behaved. Pallav, your statement is not exactly correct. You said when you put z equal to I times something, it's not analytic. It is analytic. It's just that it's not analytic as z becomes very, very large. So it's not analytic at infinity. Or strictly speaking, if you put in z equal to 1 by u, the resulting function is not analytic at u equal to 0. So that's a formal way to identify that. But that's the real point. These two, among the two functions that we have here, both have essential singularities at large values of z. However, on the real line, this is fine. On the real line, this is not. So what we did was, since this was asymptotic behavior, we just hoped and prayed that if we wrote psi as something like this, then we would be okay. But frankly, we have no right to expect we should be okay. After all, this psi is the same psi. Just by writing it in this form doesn't change anything. So what this tells me is that this f now, we wrote down the equation for that. We got this equation, the so-called Hermite equation, actually Hermite equation. But by the way, we will not worry too much about pronunciation anyway, simply because we have already, or everybody messes this up. I've been calling this psi. Does anybody know how this is actually pronounced? Is it really pronounced psi? Well, psi. No, psi with a soft S. Not really. That is, if you really were to pronounce the Greek letter, which this stands for, whether you call it psi or psi doesn't really matter. It depends on how bad your pronunciation is both ways. The actual Greek letter is almost unpronounceable. It's written PSI, but how do you pronounce PSI? It's of course not written PSI in Greek. In Greek, you just write this. The English, when they wanted to come closest to the phonetics, wrote PSI. And this really is pronounced C. Oh, no. Sorry, I can't do that. C, something like that. It's not possible for a non-Greek to pronounce it, at least as far as I know. So we all stick to either psi or psi, so it's wrong anyway. Hermite, on the other hand, was a nice, genuine Frenchman. So we all know how French letters are pronounced. At least it's easy to know because there's a standard rule for that. So we will call him Hermite because it sounds more English that way, but it's actually Hermite. Well, SCYE is not right. The pronunciation is something which simply cannot be written down in Indian by Indians or even by the English. Okay, So we won't even try. And nobody tries that, by the way. World over, nobody calls this by its Greek letter name. Everybody calls it either Shai or Psi. And you can take your pick. It doesn't matter which one you call it. Both of them are wrong or both of them are right. And anyway, it doesn't matter how you pronounce this. Hermite, of course, is the name of a person, so it's better to get it right. Anyway, coming back to this issue. This equation has a singularity at z equal to infinity. In fact, it has an irregular singularity at z equal to infinity, which you can easily verify by directly putting z equal to 1 by u. Also from the fact that since you knew Psi behaves like this, either this or this, and you've written Psi as f into e to the minus z square by 2, then f must behave either like it was z square for very large Psi, which of course means essential singularity, so the equation has an irregular singularity, or like something else which is nicely behaved, or at least so nicely behaved that e to the minus z square by 2 will dominate it. So this function, so that's the answer to the other question. Another example to the answer to the question Sharon raised. The original equation has two solutions, both of which are essentially singular as z goes to infinity. This one has two solutions, one of which is essentially singular, but the other one is not, right? At least for special values of lambda, when lambda is twice n plus 1, so that this coefficient here is just 2n, this becomes a polynomial in z of degree n, the so-called Hermite polynomial. So can anybody tell me, is the Hermite polynomial a singular function or regular function as z goes to infinity? And if it is regular, of course, there's nothing more to be said. But if it is singular, what kind of singularity is this? Pole, essential, branch point, what?
Sir, pole.
Pole, yeah, exactly. It's a pole because simply like say h1z, that's easy enough to remember, that's 2z. As z goes to 1 by u, this is 2 by u. So this is the first order pole. As u goes to 0, so this is the first order pole as z goes to infinity. Similarly, 4z square minus 2, the h2z. But actually the second order pole as z goes to infinity. In any case, the h and z will have an nth order pole as z goes to infinity. But in any case, whatever be that behavior is dominated by the e to the minus z square by 2. So that should not be an issue. Just hold on, somebody is at the door. I don't do that. Okay. So basically, the reason why I'm stressing this so much is that all the differential equations that we will meet, like we will have to handle the Bessel equation quite a lot later on when we talk of scattering, all their basic mathematical structure is in a way similar. Okay. And if you understand the basic points, you can simply repeat much of the stuff elsewhere. Not total, of course. There are differences, but the basic structure and the basic ideas that are used are the same everywhere. Okay. Any questions so far? So one more question: how much of the hydrogen atom problem have you done so far? And by this I don't mean how much you have done on your own. How much was done in class? It wasn't done in either of the two classes before. Okay, but you have done angular momentum and spherical harmonics. All these YLM functions, you've done that, right? So you have solved the differential equations to get there, or you have been just given the spherical harmonics? Okay, so that means as introduction. Okay, fine. That's okay, but we will need to know some of the mathematical properties to be able to do some of the calculations. And the good thing is, and that is why I insist that you definitely go through the lectures that I've put up on YouTube right now, because even though that they may cover things you already know, because some of those things at least are going to be sort of repeated. Okay, we solved Legender's equation explicitly in first year EM course. Good, at least. So you have seen the Legender equation being solved, but just the Legender differential equation, right? Not the associated Legender equation. Yeah, I understand that, because the first year, of course, nobody would do associated Legender. You did do Legender or Lahore. Okay, let's not be too precise about the pronunciation. Legender is fine. Okay, so we will need to discuss a bit more about those things as well. So what I will do is that in the next couple of videos, I've already prepared another video on these issues. I'm pretty sure the next video covers things which most of you already know. Things like the no degeneracy theorem in 1D. Everybody know that? That is the statement that there cannot be any degeneracy in 1D bound states. Is this known? Yes, no. Okay, I am getting opposite answers. Can we get there using Sturm-Liouville? You don't need to, you can. Not formally. Okay, fine. The other is oscillation theorem. Okay, oscillation theorem, you may not have heard the name, but that's a theorem which explains why higher energy eigenfunctions have more nodes than lower energy eigenfunctions. I mean why, not the result. Everybody knows the result. So the yes is for the oscillation theorem, I guess. I'm sorry, I see yes and no sort of oscillating in the chat box. So I can't be sure. Okay, anyway, these are parts of the next video that I'm uploading, which I should be able to do today or by tomorrow morning, I guess. And in addition to these, in this video, what we have done is I've described how you could use the GNU plot, for example, to plot Hermite polynomials for you, or how you could. Okay, let me just show you one thing. There's something which you should really see here, although I will put it in the video as well. Let's just do one thing. Okay. I hope all of you can see this, right? So what I have is a energy slider, which I can slide across. Basically, this is a solution to the Schrodinger equation for the harmonic oscillator for some arbitrary value of energy, with energy here is really the lambda. Some lambda in that lambda minus z square. I just put in 4.999 right now. I don't know whether you can see the number. It's 4.999 at that corner. And as you can see, I've started with a solution which vanishes at one end. Then for 4.999, which you know is pretty close to 5. 5 is the value of lambda for which you have the second excited state, right? N equal to 2 state. Remember, lambda is 2n plus 1. So 5 would be n equals 2. And what you see is what happens to the solution. This is just a numerical solution to the differential equation. What happens to it is it sort of looks very much like it's neatly going off to 0 on this side, but then suddenly it blows up. Why? Basically because what has happened is that in this solution there is this part which blows up, and there's also a part which behaves nicely. But the part which blows up is very much there, and it simply overtakes and blows up badly. Okay. But if I just now slowly change the energy by using the slider, I think you will see what's happening, right? So just about this value, which is 4.9999983, which is not exactly 5, but that's understandable. This is the A, because this is numerical calculation, so it's not 100% accurate. And B, because the boundary conditions we have put in is not that the wave function vanishes at plus minus infinity. We have put in the boundary condition wave function vanishes at plus minus 5. In these, 5 is pretty large, so it's close to infinity. But I'm sure if I had used plus minus 10, this would have gone closer to 5. And now you see that if it goes the other way, it suddenly starts blowing up again. So when you're very close to the actual value, even if when you're very close to the actual value, you see that when it agrees to the actual value to 3 places of decimal, you still see it blowing off right now to minus infinity very, very rapidly. Okay. I'm pretty sure you have used the basic idea behind this in programs that you wrote in the last semester. I don't know whether you have done this, but I think you have. The shooting method. Have you already done the shooting method, at least in the last semester's course? I see a no, sir, but is this for the shooting method? I can't see it. You have not used the shooting method to find out the energy eigenfunctions and eigenvalues? Oh no, that course was shifted to this semester. I don't mean the computation course. I know the computation course was shifted to this semester, and the shooting method will be there in that semester. What I mean is, in the quantum mechanics course, didn't SB ask you to write programs to find out the eigenvalues?
Yes, sir, but I don't know, like, if we use that particular method. I'm not familiar with it.
Okay, the name shooting method simply is what you saw right now on the screen. Basically, the idea is you start solving the equation from one end, okay, and try to get to zero. So when you want to start solving a second order differential equation numerically, you need to give initial values. So here what we did was given initial value that psi is 0 at minus 5 and psi prime is some value at minus 5, right? And we then shot across the whole thing and got to the other end. And then we were asking, are we hitting the target? The target, of course, is here. We want to go to 0 at the other end, but we couldn't manage to, right? Unless we got just the right value of lambda. So that was the real point. If you chose lambda to be just correct, you're aiming at the target, and now you have managed to get it. Now, this is something which I'm showing you graphically right now, but this is something which you can easily do by sort of adding some kind of problem, say equation solving routine to this. We will do this semester as well. You will do this semester in the computation course. This is very much part of that, but it's something which you can easily do on your own. It's simply just write down any routine which solves a differential equation, goes from one end to the other, and then try to see whether you're going to 0 on the other side. If you're not, then change your parameter. And basically, you treat this as an equation solving problem. That is, you want to solve for that value of lambda, which gives you the value of the wave function at this end to be 0. So treat the value of the wave function at the other end as a function of lambda, and you want to solve for this psi at the other end of lambda equals 0. And you get the value of lambda that way. But there's another reason why I wanted you to see this program in action. And that would be easier to see if you, okay, if I change the parameters a bit. Okay. By the way, all the work that is done is essentially done here. This just takes the value from the slider, then uses something called ODE int, which is a part of the SciPy, which I did not get to discuss in the last course, but we will use. In fact, I'm going to discuss ODE int with you in the computation course. And that's it. And then you just use a matplotlib to plot it. So essentially, this is where the work gets done. The rest is just to draw the slider and put a reset button and so on. Okay, so let's say the slider right now, as I put it in just because I wanted to show what happens very close to 5. I put the limits on the slider to very small values, but let's just change that. Let's say the lower limit for the slider, let's put that at 0, and the upper limit, let's put that at, let's say, somewhere around 20, let's say. Or, okay, 20 is fine. So what I want you to see is what happens for several energy eigenvalues, how this goes. So notice what is going to happen to the wave function as I change the energy. Notice what we have done is we have started with the initial conditions that the wave function vanishes at large negative values. Here I've taken -5 to be large enough, which is reasonable, but not. This will of course not be very good for higher order wave functions, because the higher up you go in wave function, the bigger the spread of the reasonably large value of the wave function becomes. So -5 is really almost -infinity for lower order wave functions, but for very high order wave functions there will be a substantial difference. So now what you do is, as you change the energy value by using the slider, first of all you notice that this wave function was going off to infinity rather badly, but now it's sort of turning a hump. And then, okay, the slider would be very difficult to control at this stage, so I just want you to appreciate that somewhere in between this and this, it was going out to -infinity, now it's going off to plus. Sorry, it was going off to plus infinity. Now it's going off to -infinity, somewhere in between, and we have just crossed 1. Remember, this theory tells us this should happen at 1, 3, 5, and so on. What has happened is you have got 1 now. You have crossed 1, and so somewhere this you would have had an exact Gaussian kind of solution with 0 on the other side. Okay, now notice what happens as I keep on increasing the energy. Okay, so now you have crossed, this is where you almost had the second excited state, you have just crossed that. So if I had used a small range on the slider from say 2.999 to 3.0001, we would have been able to pinpoint this like we did for the next case. But what I would like you to realize is that what is happening to the zeros? There were no zeros before, but now you have got a 0 here. And this function, which is going off to, this has had a 0 here, and the actual energy eigenfunction, which would have occurred at 3, would have the other 0 at infinity. But now, as you have increased the lambda, what has happened is that the 0 at infinity has moved in. So the next time you get a energy eigenfunction, which of course will happen somewhere in between these two, you would have 2 nodes in between. and then one more, and so on. Now you can see that this one is somewhere close to 19.01 or something. And you should notice that this has a pretty big slope at -5, which essentially tells you that putting the wall at -5 and saying that the wave function vanishes there was not such a great idea for this high an order. But the basic idea is that this should at least tell you how things are improving over, how things are changing as you go to higher and higher lambda. Okay. So the fact that you get more and more nodes as you go higher in energy, and the wave function changes character from being nodeless, then having one single node, going from even to odd, and so on. All these things are actually easy to visualize if you have this program with you, and you can of course write your own program. That's pretty easy. I will just give you the code in VLearn, but I'm pretty sure you should be able to write it yourself with, at least after the ODE in class is done. And well, the only tricky thing here is to get the slider to work nicely, and that's it. Other than that, it's really straightforward. Okay, but what I want you to do is sort of explore and get a feel for yourself as to what happens when the energy eigenfunction keeps on changing, or energy eigenvalue keeps on changing. Remember, it's not an eigenvalue unless the wave function actually goes and ends up at 0 on the other side. If it doesn't, then it's not an energy eigenvalue. Okay, so this is basically a way to understand why quantization occurs. You could, of course, solve the differential equation for any value of lambda, but only for specific values of lambda will you get a well-behaved, decent wave function. Okay. Any questions on this? Am I still here? Or is everybody else still here? Okay, no normalization condition imposes quantization. So normalization condition imposes quantization. No, not really. Well-behavedness, that is, it doesn't blow up, which for functions like this also implies normalization. It's really not normalization which imposes quantization. The demand that the wave function does not blow up imposes normalization. A wave function may be unnormalizable without blowing up, right? It's really an sort of interplay of all of these. You have to satisfy the differential equation everywhere. By the way, I'm pretty sure all of you have solved equations like this, right? A potential. This is an equation which you must have solved, right? That is a potential which looks like this. The finite well problem. Yeah, and what did you do here? What you did was you wrote down, you had 3 solutions in the 3 regions. I'm just sort of ad-libbing here. So you have three solutions in the 3 regions. Each of these were pretty straightforward solutions because after all, potential is constant in each of the 3 regions. You know the solution. And then you impose continuity conditions, right? At this point and this point. It insisted that the wave function had to be continuous and derivative continuous. And that gave you the quantization relation, right? So impose continuity and derivative continuity at the two ends where the potential is jumping from one form to the other, and this implies quantization. And for the harmonic oscillators, what we just said was something like this. Solve the ODE, demand that the solution doesn't blow up, and this gives you quantization. Critical question, are these two different? That is, are we using two different roots in the two cases? For the square well, what we did was we had to impose continuity, derivative continuity. For the harmonic oscillator, we had to impose the demand that the solution does not blow up as s goes to plus minus infinity, which is why we had to truncate the power series and make it stop. And that's what gave me the quantization. So are these two things different? Different in not different in the way you do it, but different in their actual physical input, in what they are really doing. Remember, there are two pieces here. You don't just demand that the solution does not blow up, you also solve the ODE, right? And then demand that the solution doesn't blow up. This is for the SHO. For the well, it seems that the demand that it doesn't blow up doesn't even enter anywhere. You just impose continuity, derivative continuity, you've got the answer. Is that correct?
No, I think we also had to impose that condition somewhere. Like we somewhere had e to the power a e to the power kz plus b e to the power minus kz, and so we had to neglect the term which was blowing up.
Well, not neglect, drop. There's a difference. You can't neglect a term which is blowing up, right?
Yeah, we had to drop.
You have to just
We had
drop
to
if it's
drop
there.
that.
Yeah. So you had a positive. So Shahid is also saying the same thing. Although here you have to keep it to the plus. You have to drop the to the ax term. Here you have to drop the to the minus ax term. Because these are the two solutions which will blow up as x goes to plus minus infinity. So here, of course, you did make the demand that the wave function stays well behaved and does not blow up. So that demand is very much made in this case as well. The only point is here you did it even at the you did it at the beginning simply because you knew the exact form of the solutions. Here the equations in the three pieces were so simple that the way in which you handled the problem was different. You knew the solutions, so you could just pick out, okay, these are the ones which are going to blow up, so we will drop them at the very beginning. Okay, so you have to impose well-behavedness in both cases. But what about this continuity, derivative continuity? Scattering states, the terms were there and so on. We are not going to talk of scattering states now. We are going to definitely going to talk of scattering states a lot when we talk of scattering. But we are talking of energy bound states right now. So let's not go into that right now. You're right, although that's a different kettle of fish altogether. And requires a lot more advanced math to make those things meaningful. So we are not going to talk about that. Not now. But the question I have for you now is, this imposing continuity, derivative continuity, this thing seems to be very different from what you do here. Here you had no such need, right? Is my presentation still visible? I'm asking because I momentarily lost
So we
that.
can see your screen.
Yeah, that's fine. Can you see this now?
Yeah.
Because I momentarily lost contact, so it's back before it did any more damage, it seems. So the question I still have is this imposing of continuity, derivative continuity. The potential was continuous, so it was inherent in the solution. Okay, that's actually, I guess, the meaning of what you're saying is right. The point is, in both cases, you're solving the ODE. The ODE meaning whatever you get from the Schrodinger equation, both for the simple harmonic oscillator and for the well. For the well, it so happened that the three pieces in the three regions for x less than a and x greater than b, in this region and this region, the equation, and in the region in between, the equation was easy to solve. However, the important thing is we are not in the business of solving the equation in these three regions. We have to solve the equation everywhere. This is critically important. You have to solve the equation for all x. And piecewise solutions, which are solution here, and solution here, are actually not solutions of the Schrodinger equation. It becomes a solution of the Schrodinger equation only if the pieces match to each other properly. Okay, and matching here means you have to impose continuity and derivative continuity simply because that's what the second order differential equation would do for you. If in fact you had solved this problem numerically, you wouldn't have to do anything of this kind. You could solve this problem numerically just as well, and you would find a solution which looks essentially almost like what you saw a while ago with the harmonic oscillator. If you did a numerical solution of course does not care for matching the derivative or continuity of the derivative because that's imposed by the numerical solution routine itself. And even for the well, you could very well use the shooting method or essentially do the kind of thing that I did a while ago. The only point is here, because the individual pieces were easy to solve, we solved them first. We also imposed the well-behavedness demand by dropping these exponential solutions, parts of the exponential solutions. And then we realized that, okay, even doing that does not give me a solution. To get a solution, what I need is something where the three individual pieces match properly. Why? Simply because your equation is psi double prime equals some function of x into psi, ultimately, then psi prime has to be continuous. Otherwise, psi double prime will not exist. And if psi prime is continuous and exists, then psi has to be continuous. That's something which follows from the differential equation itself. Sometimes we relax one of these conditions, say when your potential has a delta function kind of discontinuity. Then psi prime may have a discontinuity, but that's dictated by the equation itself. So this imposing of continuity, derivative continuity is just a way of solving the differential equation. So basically, when you solve the ODE for this, individual pieces are straightforward, but solving the ODE proper means that you also have to have this. So if you really think about it properly, in both the cases, you're actually doing the same thing. You are actually solving the ODE and demanding that the wave function stays well behaved at plus minus infinity. Okay? So the method of solution may look very different depending on what kind of simple tricks are available to you. However, the real ideas that are used are exactly the same in all such cases, not only in these two cases. Solve Schrodinger equation, demand the solution is well behaved. And it so happens that unless the solution is unless the energy takes certain values, the solution ceases to be well behaved. And that's where quantization comes from. Okay? So any questions on this? Okay, next, again, a question about what has been done so far. You have I think several important topics in the previous course could not be touched upon. Of course, depending on time constraints, especially also because of the online thing, we are going a bit slower. So some of those things we will have to do because they are way more important than some of the topics that we have in this course. So at the very outset, let me tell you that some of the topics that you see in the syllabus in this course will not be covered for two reasons. One, there are more important topics from the previous course which has not been touched upon yet, and they have to be covered. And this is your last formal quantum mechanics course, purely quantum mechanics course. And the other reason is that many of these topics are also available for you to study in the atomic physics, atomic molecular and optical physics course, which has been started from this year, which will be available to you next year. That's an elective course. You don't have to take it, but if you want to learn about those things, you will definitely get a chance to learn about those things. More importantly for us, many of those things will also be treated in this course, but more as a sort of application of some of the more general results we have learned. But the approximation methods of quantum mechanics, which are very important. After all, very few quantum mechanical problems can be solved exactly. So approximation methods, how many have been done so far? So let me just rattle off the names. Variational method. I know perturbation has not been done, right? Perturbation hasn't been done, I know. Variational has not been done. Is that correct? Okay, don't say no, sir, because not done. Okay, that's more explicit. Variation is not done. Okay, variation has not been done. JWKB or WKB?
Sir, none of them have been done, I think.
Okay, so we will start with the. Okay, so what we will do is in the next week also we will just try to complete up to the harmonic the hydrogen atom, but that will be at a much faster pace. I will not do all the steps, but for the simple reason that most of the steps are very similar to what has been done for the harmonic oscillator, and the basic mathematical ideas are the same. I will just indicate the basic mathematical ideas in the video. I will describe the solution, and I will set problem sheets where you will fill up the rest of the steps. Okay, so that's the program for the next week. Then we are going to start with approximation methods. And for that, let me just ask you one more thing. Contour integrals, you have done contour integrals already, right? In complex analysis, yes. Have you done contour integrals involving branch points? Or just poles?
Sir, only poles.
Okay. So you use the residue theorem, right? You know the residue theorem.
Yes, sir.
And I used the Cauchy integral formula in the second lecture. Are you familiar with that? Okay, good. So I need to know this because I need to know what to put in and what not to bother about. So, okay, fine. So you know, and you also know that you can deform a contour as long as you don't cross a singularity and so on. All this stuff you know, right? Okay, good. So, because all this is going to be useful for these approximation methods as well. So once we once we indicate how the hydrogen atom problem is solved, we are going to talk about variational first. Oh no, maybe we'll talk about perturbation first, then variational, then GWKB. After that, we are going to do identical particles has been done?
Yes, sir.
Okay, good. And symmetries, you have done rotational symmetry a bit because I know because of that time when SB asked me about it. But
Sir, space translational and time translation symmetry had also been covered by Shumitra, sir.
Okay, good. So that's okay. So I will not have to deal with a lot of that. Fine. Okay, then we'll do something about the symmetry, small amount. Then we will try to move on to second quantization, at least the basics of second quantization quickly. Then do scattering theory, or maybe the scattering theory will come first. The scattering theory has to be covered, so maybe I will do that before second quantization, and then if we have time, we will touch upon the other topics as well. But all this will take a lot of effort. Will you also solve for angular momentum eigenstates? You mean the wave functions? Do you mean the spherical harmonics? Well, I will show you how to do that. That's part of the Hydrogen-Adams solution in a way. But I will not solve every step. But I don't need to, I guess, because you already know the methods. I will just try to point out, as I did in the harmonic oscillator case. By the way, did you already know about this singularity stuff as to exactly why you were doing this e to the minus z square by 2 and why you knew already that e to the z square is a possibility for f of z? Do you already know all that? But you should, because okay, this is a kind of thing you should be sort of aware of when you're trying to solve a differential equation like this. So I will essentially indicate those issues, the potential pitfalls, how to handle them when I talk about the equations for spherical harmonics. I've already solved the legendary equation, but okay, can you tell me one thing? The legendary equation, as you all know, is of this form, right? d2p dz2 plus 2z dp dz and so on. Lambda in L into L plus 1 into P or whatever. And this has a singularity at z equal to plus minus 1, right? But can anybody tell me why is there a singularity at z equal to plus minus 1? I don't mean from the equation, but from where the equation came from. If you remember z, I hope you remember this, right? This z was not the z coordinate. This z was the cosine of the angle theta. So this angle theta of the theta phi r, the spherical polar coordinates, this z was cosine of theta, and you wrote down the differential equation. Essentially, you wrote down Laplacian in spherical polar coordinates, and you ended up with, after separation, you ended up with an equation involving theta, which you changed to an equation involving cos theta, and you ended up with 1 minus z squared d2b dz2, etc., etc. The first question that I have for you is this. You did this substitution and not this one. Any idea why? Why didn't you choose sine theta? That sounds... Sine theta seems to be the one we use all the time, right? Cos theta doesn't seem to be everybody's first choice. So why did we use cos theta there? Theta, remember, is this angle, the angle from the z-axis. Yes?
Can I tell that? Because I choose z equal to plus minus 1. For z equal to plus minus 1, theta value is minus pi to plus pi. So this means this in the real line, real axis.
You mean the z-axis?
Real axis.
This is 3D. There's no complex here. You mean the z-axis. Fine. Good.
Yeah.
Then, so what's the problem with the z-axis?
Real axis.
Is just like...
Real axis.
No, this is a 3D, right? There is an x-axis, there's a y-axis, there's a z-axis. And you're saying, you have rightly said that theta equal to z equal to plus minus 1 means theta equal to 0 or pi, which means the positive z-axis or the negative z-axis. So far, I agree with you. My only question to you is, why is there a problem? Why should there be a problem on the z-axis?
But so if I choose sine theta, so function...
No, wait a minute. Are you trying to answer why cos theta and not sine theta, and why, or yeah, if you choose sine theta, what will happen? All right.
So in the y-axis. So that means
So what's
that's
your problem? Then it says y-axis will have zeros or whatever. So why is that a problem? But you are going along the right directions. But
and so about the poles, sir. There is a problem with the pole.
yeah, but why is there a problem with the pole? Well, first of all, cos theta and sin theta. I think everybody knows this, so I don't think I should really have to draw this. But this is a sin theta graph, right? From 0 pi to pi. And cos theta looks, with my horrible drawing, it looks, okay, it doesn't look good at all, but anyway. Doesn't at all look like this, so let's. Oops. And cos theta essentially looks like this. It goes to 0 here, -1 here. Z bar is not analytic. Unfortunately, I think you have been misled by my notation. This Z is not a complex number. Z bar is not its complex conjugate.
Is this
This Z
because
is, I just used,
uh,
I wrote Z bar
this
simply
because-
because I was talking of sin theta. Yeah.
sir, from theta equal to 0 to pi, sin theta
Yeah.
covers only positive values. Cos
Yeah.
theta both covers positive and negative values.
You are moving in the right direction, but not really. Because why am I bothered about something? Why do I want that to be also negative? Why is only positive bad? Sorry, Shahan, I couldn't see. Okay, let me just check what you said. I couldn't see the whole thing. Yeah, Good Powell already has the answer.
Sir, can I tell you? Because in the z to plus minus 1, there is a singularity, sir.
There are two different questions here. So which one are you answering right now?
Is why I choose cos theta function.
No,
not
that is actually the answer. You gave the right answer to the other question, but I'm not sure whether you did it understanding. The point is really the substitution, as Gurbahul has pointed out. First of all, theta goes from 0 to pi, right? That's the range of theta.
yes,
So
sir.
you're only worried about this much. You're not worried about the rest of it. Okay. And over this interval, sin theta is not a one-to-one function. Being only positive is not the problem. The real problem is it bends back and comes back here. So for every value of theta, for every value of sin theta, there are two values of theta, right?
Yes.
So it's not a one-to-one function. Cos theta, on the other hand, is a one-to-one function from 0 to pi.
Oh,
Which is why cos theta is the correct substitution to make, not sin theta.
yes, sir.
We tend to forget, we don't even stress this very often, that say when you do substitution of variables in an integral, it's very important to check that your substitution is one-to-one, because if it at least over the range over which the integral is being done. Because without that, substitutions don't have any meaning. Okay.
Yes.
So the sin theta curve, sin theta is simply not a one-to-one function from 0 to pi. And 0 to pi is the correct range for theta. So you can't change that. So you have to use cos theta anyway. That's one point. The other point is, why do you have a singularity at z equal to plus minus 1 or cos theta equal to plus minus 1? Of course, you might say the equation shows that there is a singularity. My question is, could I have anticipated the singularity before solving the equation? Or before even writing down the equation? Could I have anticipated that something might very well go wrong there? Remember, the equation, the coordinates you're using are r theta phi. And the question I have for you is this a decent coordinate system? Is this a good coordinate system? I hope everybody understands what it means to say that something is a good coordinate system. Yep. So there are two answers on the chat box. Both of them are correct. But the basic point is a good coordinate system is one in which they have a bunch of coordinates, in this case 3, because we are in 3 dimensions, which are in one-to-one correspondence to the points in your set. Which means every point has 3 coordinates, and every 3 coordinates correspond to a unique point. There's a one-to-one correspondence between the two. That is true for the Cartesian coordinates. Cartesian coordinates are good everywhere. No matter where you are, okay, in 3-dimensional space, x, y, z uniquely points to a given point. Of course, that means that you have already chosen your origin, chosen your axis, and so on. But once you have done that, every point has a set of good coordinates, right? Every triplet of numbers corresponds to a point. Every point corresponds to a unique triplet. That doesn't happen for spherical polar coordinates. For spherical polar coordinates, theta equal to 0 or pi are bad points. Why? Because there are infinitely many phi values. When you are on the z-axis, what is your phi? Any phi will do, right? You could say phi is undefined, or you could simply say phi is indeterminate. That's a better word. It's like 0 by 0. 0 by 0 is really indeterminate because any number would fit 0 by 0. Right? 0 by 0 means what? 0 by 0 is the answer to the question, what number is it when I multiply it by 0, I get 0? And the answer is any number will do. That's why it's really not infinite or undefined in that sense. It's really indeterminate. Every number would fit this. That's why we don't talk about this. Similarly, at theta equal to 0 or theta equal to pi, you're on the z-axis, and there the value of phi is indeterminate. So there are infinitely many different coordinates which correspond to the same point, right? You would take r equal to 3, theta equal to 0, and phi equal to, say, pi. That talks about a point, r equal to 3, theta equal to 0, phi equal to pi by 6. Same point, right? Not only does these two, put in any arbitrary value of phi, you get the same point, which is why you have a coordinate singularity there. The problem is not with the point itself, the problem is with the coordinate system that you have chosen. Okay. So even if there were no other physical problem with that point, if you're using spherical polar coordinates, you expect trouble at theta equal to 0 and theta equal to pi, or cos theta equal to plus minus 1, simply because you're using a coordinate system which goes bad at those points. Does not look like it's going to go bad really if you don't think about it carefully. Okay, I seem to have stopped my presentation anyway. But anyway, I was just scribbling bad pictures on the screen, so maybe it's a good thing that nobody saw the nasty pictures I was drawing. But anyway, let me just quickly move on to the next page so that. So I hope it's visible now. So what I was saying is something like this. This is your theta angle. And if you ask how much you're turning your xz plane to go through your point, whatever that point P is, that's your phi, and this distance, of course, is r. So when you're on the axis itself, any value of r, let's say r is equal to 3, theta equals 0, and no matter what phi you choose, any phi, will talk about the same point, namely this one. So there are infinitely many coordinates which actually mean the same point, right? So the one-to-one correspondence between points and coordinates breaks down on the axis, which is why whenever you try to use spherical polar coordinates to find out equations, you anticipate that there will be trouble at theta equal to 0 and theta equal to pi, even before you write down the equations. Even if there is nothing in the physics which gives you trouble, the coordinates themselves will. But also you should realize that that is the reason why that trouble can be circumvented, right? After all, coordinate singularities are simply there because you are using bad coordinate systems. There's nothing physically bad about those points. So there will be trouble, but there will be ways out of the trouble as well. So should not be a problem to it should not really be a problem to avoid the singularities that arise. Which is also in a way seen by the fact that the singularities that you get are not really that bad as the one in the harmonic oscillator. It's not an irregular singularity, it's a standard regular singularity. And finally, there's another point which is even more singular. Which one is that? That is, if you're using spherical polar
Origin.
the origin is horribly singular, right? Origin has only one thing that you know about it, r equal to 0. Any value of theta, any value of phi, you still have the origin, right? So you expect, even without any calculation whatsoever, that r equal to 0 is a potential trouble spot when you are using spherical polar coordinates. Okay? You have to use spherical polar coordinates when that's the best way to describe your potential. Fine. You can't avoid that. But you have to be aware beforehand that whenever you're using spherical polar coordinates, r equal to 0 will give you trouble. Theta equal to 0 and theta equal to pi will give you trouble. Not because of any physical problem. Of course, if your potential has a singularity at r equal to 0, like say it's a 1 by r potential or something worse, then the trouble only gets worse. Okay? But even without that, even for the free particle, r equal to 0 is troublesome. Why? Because r equal to 0 is a core, but then the trouble is not really unsurmountable because that trouble really isn't there. The trouble is simply there because you're using a coordinate system which goes bad there. That of course says that physics is okay. It's just that your description of the physics using your coordinates that may have a difficulty. Okay. So the fact that r equal to 0 is a singular point for say the hydrogen atom problem, that of course comes not only from the coordinate singularity but also comes from the fact that that you have a singularity because of the potential itself. But even without that, say a 3D harmonic oscillator where there is no singularity at r equal to 0 in the potential, still will give you a singularity at r equal to 0 because of the bad choice of coordinates there. Okay. For the harmonic oscillator, of course, if it's an isotropic harmonic oscillator in 3D, you have done this problem, right? The 3D harmonic oscillator, that is a potential which is half m omega square. Have you done this problem? Yes? No? Yep. Okay. So this one is easy enough to do in Cartesian coordinates, of course. And in Cartesian coordinates, you will find no problem whatsoever. But it's also obvious why you might want to do it in spherical polar. So the potential simply looks like this. And this potential is perfectly nice at r equal to 0, no singularity at all. But if you were to solve this problem in spherical polar coordinates, which you would want to often, it is one of the simpler problems you can solve in 3D. The problem can be solved. The only point is there will be some issues which you have to face at r equal to 0, not because of the potential singularity, there is none, but because of the coordinate singularity. So all I'm saying is these are the issues which you have to pay attention to whenever you're solving equations of this kind. Okay? If you know this beforehand, you're forearmed, and hence you can actually handle these things much better. Okay? So unless there are some other questions, are there?
Yes, sir. It's about the, I mean, course in general. Like the grading method will be the same as last time.
No, I wrote down the grading method in the mail. Did you see that? It will not
Oh,
be
okay,
exactly the
okay.
same because this time we will have midterms and endterms by proctoring if they happen. Now, if the proctoring fails, so the thing which I send you in the mail is what do you call it? Provisional. If proctoring doesn't work out, it may not work out for several reasons, including the fact that we, being a government agency, have to go through all these hassles of taking necessary permissions and so on, and that might take time. So if that doesn't go through, then the grading method will change. Otherwise, 20 for midsem, 40 for endsem, and 40 for internals, out of which 20 will be quizzes, 20 will be 15 will be assignments, 5 will be, well, if I like your face, you get 5. If I don't, you get 3. Wait, that's not really true, but anyway, that's what it would look like to you. Okay?
Okay, sir.
But all that is provisional depending on how things unfold. And if things improve so much that you can come to the campus and give the endsem, then the endsem might even go back to 50. But that will depend on what the Senate decides. Okay? So let me just stop the recording now.